Hello, folks. Today is the 27th of April, and what we're going to do in today's video is we are going to go over what I had assigned the other day, just to make sure that we're sort of on the same page for it. I wanted to see how you guys could do without me, but I also want to, make sure that you understand what is happening here. So we're going to go over it in this video, and then there'll be a shorter assignment after the video for you guys to complete. So the first thing that you guys had to do was this opening exercise over here. The opening exercise starts with a murder. The detective is called to the scene of a crime where a dead body has just been found. He arrives at the scene and measures the temperature of the dead body at 9:30 p.m. After investigating the scene, he declares that the person died 10 hours prior, so 10 hours ago, at approximately 11:30 a.m. Crime scene investigator arrives a little bit later, CSI person, and declares that the detective, no, you're wrong. I don't know why you would think that. She decides to say that the person died at approximately 6 a.m., 15 and a half hours prior to the measurement of the body temperature. She claims that she can prove it using Newton's law of cooling, which we have an equation for right here. Newton's law of cooling is just an equation that helps you tell how long something has been cooling down from when it started. So we have T of T, so our function of T is equal to T sub A, that's what we call that when it's down there, plus, parentheses, T sub O minus T sub A, times 2.718 to the negative KT power. Now, just looking at that honestly is an equation that might not make too much, I suppose, sense to us just from looking at it. However, lucky for us, they decide we're going to give you a couple of guidelines that's going to help you understand what each of these mean. T of lowercase t, because we have uppercase and lowercase t's here, is going to be the temperature of the object after a time of T hours has elapsed. T sub A is our ambient temperature. But what does ambient temperature mean? Ambient temperature is how hot or cold the temperature of the surroundings is. And we assume that the temperature of the surroundings is going to be the same temperature the entire time. T sub 0 is our initial temperature of the object, which is our temperature at the start. Initial means start. So initial temperature is going to be our starting temperature. And K is going to be our decay constant. Our decay constant is something that's really going to depend on exactly what is the thing that is cooling. It's going to depend on a couple of different things. Luckily, we don't need to find out what K is. They tell us what K is. Using data collected at the scene, we need to decide which of them is going to be correct, our detective or our crime scene investigator. Well, we have our temperature of our room, 68 degrees Fahrenheit. We have the initial temperature of the body, 98.6 degrees Fahrenheit, because that's just the normal human body temperature. And then K is going to be 0.1335, which is 13% an hour. This was calculated by our investigator. the temperature of the body at 9:30 p.m., which is when the dead body was discovered, is 72 degrees Fahrenheit. So, what we are going to do is we need to find out which of these two people, a detective or a crime scene investigator, which of them has a better, I suppose, guess or estimate as to what their starting time is. So, what we have is we have our detective who says 10 hours, and we have our crime scene investigator who says 15 and a half hours. So what we're going to do is I'm going to take this equation and I'm going to plug in 10 to it, and I'm going to plug in 15.5 to it, and I'm going to see which of them gives me a closer temperature to 72. So T sub A, my temperature of my room is going to be 68 plus 98.6 minus 68 times 2.718 raised to the negative k, which is 0.1335 times t. So for our first person, our detective, that t is going to be 10. Now, if we take this and plug it into a calculator, which is what we would be doing in this case, we are going to get right around 76 degrees Fahrenheit. If I was to round this to my nearest whole number, we're going to get 76 degrees Fahrenheit. 76, well, I mean, that's pretty close to 72. Not the closest, but it's pretty close. Well, to compare, let's do the exact same thing, but with what our CSI investigator said. If our CSI investigator is closer to 72 degrees, that means that she is right. If not, our detective is right. So, most of our equation is going to be the exact same. 68 plus 98.6 minus 68 times 2.718 raised to the negative 0.1335 times, in this case, instead of multiplying by 10, we're going to multiply by 15.5. Because our CSI investigator says, I think it was 15.5 hours, 15 and a half hours. So we need to test what 15 and a half hours is. If we were to take this, plug it into our calculator, making sure to be careful and making sure that all of our parentheses are in the right place. We're following order of operations with everything. We're going to get 71.865. Which, if I were to round it, just like how I rounded this one to 76, it's going to be right around, oh, look at that, right around 72 degrees Fahrenheit. Well, what do you know? Our CSI investigator says, no, it was probably around 15 and a half hours prior to this. The body Temperature right now is 72 degrees. The body temperature that would be if 15 and a half hours pass by is 71.865. So she's not exactly right. It's not exactly 15 and a half hours. But my God, that's super close. Even if it's not down to the second, 15 and a half is basically the 100% correct answer here. We would only be off by maybe just a few minutes. So that's our opening exercise. For opening exercise, we just had to take the data that we know and plug it into that equation to see which of them was closer to the result that we wanted, 72 degrees Fahrenheit. Now what we're going to do, we're going to get into the actual mathematical modeling exercise. There were three sort of parts to this. And they decided, you know what, let's go with a slightly less morbid scenario for our modeling exercise. Instead of talking about a dead body found at a crime scene, this time we're just going to be talking about some coffee. We have 2 cups of coffee that are going to be poured from the same exact coffee pot. The initial temperature of the coffee is going to be 180 degrees Fahrenheit. It's always going to be 180 degrees Fahrenheit for all 3 scenarios. And K is 0.2337. It's going to always be that if we're talking about time in minutes, which, good news, we're talking about time in minutes. So these are 2 things that we're going to need to keep in mind the entire time. We are going to, for scenario 1, we're going to suppose that both cups are going to be poured at the exact same time. However, cup 1 is left sitting in a room that is 75 degrees Fahrenheit, and cup 2 is taken outside, where it is instead 42 degrees Fahrenheit, so not nearly as warm as inside of the room. Part A says, hey, use Newton's law of cooling to write equations for the temperature of each cup after T minutes have elapsed. So we're going to use this exact equation over here, and we're going to plug in some of the information that we know. Remember, we have T of T. This is something we don't know yet. We don't know what T is. Everything else is something that we know. So we're going to have 2 different equations here. One for cup 1, which will be in blue, and then cup 2 will be my red equation. For our first cup, well, let's look at everything. We have our initial temperature. Our initial temperature is T sub 0. So T sub 0 is going to be 180 degrees Fahrenheit. Our ambient temperature, aka our temperature of our surroundings, cup 1, we have right here, it's left sitting in a room that is 75 degrees Fahrenheit. So our ambient temperature is going to be 75 degrees Fahrenheit. And then the last thing that we know is that K is always going to be 0.2337. Now we can take all of this and make the equation. Temperature in regards to time is going to be equal to T sub A, so 75, plus T sub 0 minus T sub A, so our starting temperature minus our temperature of our room, times 2.718 to the negative K, which will always be 0.2337 times T. So there's our blue equation. For our red equation, for our cup 2, most of our pieces are going to be the exact same. In fact, our initial temperature is the exact same. Our K is the exact same. The only thing that is going to be different in our equation is instead of our ambient temperature, our temperature of our surroundings being 75 degrees Fahrenheit, our temperature of our surroundings is going to be 42 degrees Fahrenheit, because this cup is taken outside. One person wanted to sit inside while they were drinking their coffee, and the other person wanted to go outside and enjoy the semi-decent weather. Not the best, but if you've got a hot cup of coffee, it'll be fine. So our equation is going to mostly look the same, except all of our 75s are going to be replaced with 42s. T in regards to T, our temperature in regards to time, is going to be 42 plus 180 minus 42 times 2.718 to the negative 0.2337 times T. So we have our two equations. What we would do now with our two equations is we are going to take these and we are going to graph them. Again, if you do not have a graphing calculator, you can always go to Desmos and it'll help show it off. I'm going to do a sketch of what our graph is going to look like. I'm going to label some of the key points just so that I know them as a reference. For when I'm drawing my line. So my line for cup number 1 is going to look something like this. And again, this is a mostly sketch with some key points plotted to help me sketch it a little bit better. And for my red cup, number 2, it's going to have the same initial temperature, so they're going to still be touching at that point. But then things are going to start to get pretty different pretty quickly. So as you can see, our two graphs, despite having so much in common with one another, are going to look pretty different from one another. What's the first thing that we can notice that's different about this? Well, this one starts falling at a much faster rate. So what we can say, cup 2 starts decreasing at a faster rate. Where does it look like our blue graph is stopping? If we had to make a guess, where does it look like it's flatlining? That's somewhere in the 70s, maybe. Maybe like 74, maybe like 76. Man, if only there was a specific number that we knew of in the 70s that has to do with cup 1. We do. 75 degrees. Cup 1 starts to flatten around 75 degrees. Never going to exactly hit 75 degrees, but it's going to keep getting closer and closer and closer to 75 degrees. Where do we think cup 2 is going to stop then? Well, based off of our graph and based off of what we know, it's probably going to be right around 42 degrees. The cup 2 is going to start to flatten around 72 degrees Fahrenheit. Part C, even though it's not technically written here, Part C asks us, hey, it tells us that coffee is safe to drink when it's below 140 degrees Fahrenheit. If you drink it before then, you might burn your tongue, you might burn the roof of your mouth, you might burn your throat. It's safer to wait until it's around 140 degrees. Estimate how much time elapses before each cup is safe to drink. Well, in order to do that, we're going to need to find where 140 is. It's going to be right here. And what we're going to do is we're going to basically draw a line across. And see where it hits our graph. And again, since this is an estimate, we don't need to plug it into any calculators and get an exact number. We're basing our estimate off of where our graph lands. So even though mine is sort of a sketch, we could still make some sort of an estimation. My estimation might not be the same that you had because our graphs might not be exactly the same. So for our cup 2, because it hits cup 2 first, let's talk about cup 2 first. For cup 2, it's going to hit at right around 1 minute. I'm going to put around 1 minute. For cup 1, our blue line, let's see where it hits our blue line. For our blue line, right around 2, maybe 2.2, we'll put at around 2 minutes. And again, my estimates and your estimates might not be the same because our graphs might not look exactly the same because, again, mine is a sketch, whereas yours might not be as much of a sketch, or yours might be even more of a sketch than mine. As long as it's based off of your graph, that's what matters most. Next scenario with our cups. Both cups are going to be poured at the same time, and they're both left sitting in the same room. Okay. However, instead of being in separate rooms, so having separate and different ambient temperatures, this time milk is immediately poured into cup 2, which cools it down to an initial temperature of 162 degrees Fahrenheit. So instead of starting at 180, Our cup 2 is going to be starting at 162. Well, here's the thing. Our blue cup, our cup 1, is going to be the exact same cup as last time. So our blue cup is going to be temperature regards to time is equal to that 75 plus 180 minus 75 raised to the negative, nope, that's not the part that's raised. It needs to be multiplied first. Times 2.718, and that is raised to the negative 0.2337 T. For our cup 2, most things are going to be the exact same as cup 1. But this time for cup 2, we have an initial temperature change. Our initial temperature is going to be 162 because of the milk that we poured in. It's 162 degrees Fahrenheit. So, for cup 2, our temperature in regards to time is still going to be equal to that 75 plus 162 minus 75 times 2.718 to the negative 0.2337 T. So our two equations are, well, pretty similar. This time, however, instead of changing our ambient temperature, our temperature of our surroundings, we changed the initial temperature. Well, what we could do is we can plot these just like we plotted the last one. Good news, our blue graph is going to be exactly the same as our previous blue graph. So let me plot a few points that are going to be sort of reference points for me when I'm sketching the graph. And then let's sketch what it's going to look like. And there's that. For our red one, instead of starting up here at 180, we're going to start at 162, which is going to be 160, but just a little bit above 160. Just a tiny bit. And then I'm going to plot some more points that are going to be reference points for my sketch. And as you can see, there's a big difference between this pair of graphs and the pair of graphs that I had over here. Unlike before, they're both kind of decreasing at the same rate. In fact, cup 1 decreases at a slightly faster rate. Very slightly, but it technically gets down there faster because they both get there at around 25 minutes. But our red cup started at a lower temperature, so cup 1 got there quicker. But cup 1 and cup 2 both level out at the same temperature, right around that 75. They're both going to be leveling out at 75 degrees. Now, again, there is another question that technically isn't posted up here. So that question C, once again, says that our best temperature to drink the coffee at is going to be 140. It's going to be right around there. And we know that it should be the exact same as what we said for our cup 1 over here. So right around 2 minutes, right around 2 minutes. Yeah, right around 2 minutes. So for cup 1, it's going to be 2 minutes still. That means that our sketch here is basically the same as our sketch before. But what about for cup 2? Oh, well, cup 2 does it a little bit quicker. Right around maybe 1.5. Right around 1.5 minutes. But since they both are in the exact same environment, they're both going to sort of level out at the same temperature. Even if they had different starting temperatures. For question number 3, suppose cup 2 is poured 5 minutes after cup 1. We're going to assume that the coffee is going to be 180 degrees when we pour it in to the second cup. And they're both going to be sitting in that room. This is 75 degrees Fahrenheit. So, as per usual, our cup 1 is going to be the exact same. Cup 1 is still going to be temperature in regards to time equal to 75 plus 180 minus 75 times 2.718 raised to the negative 0.2337T. So that's going to be cup 1. Cup 2 is poured 5 minutes after cup 1. How do we show off that 5 minutes have passed? Well, basically, what we need is that cup 5 over here is going to be at 180 at 5 minutes as opposed to at 0 minutes. Okay. So what we're going to do is we're just going to take T and we're going to go minus 5. So 5 minutes is going to be where my initial graph was at 0 minutes. And since we know our initial for cup 1 is 180, at 5 minutes for cup 2, it's going to be where cup 1 was. So in fact, our two graphs are going to look very similar. In addition, their equations are going to look decently similar as well. Not exactly the same, though. There's going to be one key difference right at the end. So we have t of t is going to be equal to, they're in the same room of 75 degrees, plus, they both have the same initial temperature of 180 degrees, minus that room temperature again, times 2.718 raised to the negative 0.2337. But instead of that being multiplied by t, it's going to be multiplied by t minus 5. Which is basically, again, it's going to say that at 5 minutes, my second graph is going to be where my first graph was at 0 minutes. At 10 minutes, my second graph is going to be where my first graph was at 5 minutes. Oh, well, let's plot our first graph. And again, our first graph is going to look identical to what our first graph has looked like every single time so far. All the same classic points that we know and love, plotted right there for us. Now, what we know is that our second graph at 5 minutes is going to be where our first one was at 0 minutes. At 10 minutes, it's going to be where our first graph was at 5 minutes. At 15, it's going to be where our first graph was at 10 minutes. At 20, where our first graph was at 15 minutes. At 25, where our first graph was at 20 minutes. So quite literally, cup 2 is cup 1 shifted right 5 units. All we did to get our cup 2. The big question is, why does this cup not go up further? Why does it start here? Ask yourself that for a few seconds before I give you the answer. The answer for why it starts right there is cup 2 wasn't poured until 5 minutes passed. It didn't exist before 5 minutes. I mean, the cup itself existed, but the cup of coffee did not exist before that point. So we start our graph here. We're not going to start our graph all the way over here. So with that, we've gone over what you guys were doing yesterday. I have posted up onto Schoology the sort of exit ticket for this lesson. That's what you are going to work on today after you have finished this video. With that, I was about to say I'll see you guys tomorrow, but I guess I won't see you guys until Friday. Have yourself a great rest of your day.